Now we look at section 6.4, where we are going to talk about the complex exponential. So we know that the exponential function f of x, which is equal to e to the x with x a real number, is a fundamental object in mathematics. It's one of those functions which you will encounter in almost every area of mathematics. And in this section, we are going to show how e to the z is defined for complex numbers, right? So in the case that we know x will be real, so we want to find out what happens if z is, if the power is what, a complex number. And this leads us to definition 6.4.2. So for a complex number z which is equal to a plus bi, we define e to the z to be the complex number e to the z, which is equal to e to the a, e to the real part of z, times cos the imaginary part of z plus sine the imaginary part of zi, and that becomes our exponential of z. So as a remark, if the complex number z, which is equal to a plus bi, is a real number, that is, if b is equal to 0, then we know that e to the z will be equal to e to the a times cos 0 plus sine 0 I, which is equal to e to the a, because cos 0 will be equal to 1 and sine 0 is equal to 0, right? So therefore our definition of complex exponentiation is an extension of the familiar real exponentiation, right? So we have seen here that our definition here is consistent even when the 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 z that we are talking about is a real number, right? So that's what we have there, and we're going to look at some properties that are in theorem 6.4.3. We know that these properties are true for real exponentiation, so we want to look at them and see if they are true for complex exponentiation, right? So let z and w be complex numbers and n be an integer. Then the following statements are true. E to the z is equal times e to the w is equal to e to the z plus w, and then e to the z to the power n is equal to e to the nz. And so these properties, we know that they are true for real numbers if the exponentials here are real numbers, and theorem 6.4.3 says that they are also true for complex numbers, and the proof is left as an exercise. That's exercise 6.4 number 1 in the textbook, right? So let's look at some points to note in conclusion of 6.4. So the complex exponential provides a convenient way in which to express the polar form of a complex number. In this regard, we observe that for a real number theta, we have e to the theta I is equal to uh, e to the 0 times cos theta plus sine theta I, right? Because if we think about theta as a real number, it can be written as uh, 0 plus theta I, right? So you notice that here we were saying b is equal to 0. In this case we are saying sorry, in this case we are thinking of a to be the one that is equal to 0, and then the other part is, the imaginary part is not 0. So e to the theta I will become to will be e to the 0 plus theta I, and so therefore it becomes e to the 0 times cos theta plus sine theta I, which is equal to cos theta plus sine theta I. And thus for a complex number z, which is equal to r cos theta plus sine theta, in polar form we have it as z, which is equal to r times e theta I, right? And from this point onward we adopt the notation in 6.3 for polar form of a complex number. And note that the complex formula for z given in De Moivre's theorem 6.3.9 reads z to the n is equal to r to the n e to the theta I, right? In the newly adopted notation, I think here there is something missing. It's n theta I here instead of theta I, right? And then the identity 6.2, so 6.2 is that one, uh, implies the fundamental theorem, the fundamental result in mathematics known as Euler's identity, which connects four of the most important constants in mathematics. And the four constants in mathematics are E, pi, so there's E, there's pi, there's 1, and then there's 0. Those are most important constants in mathematics. And it reads e to the theta I plus 1 is equal to 0. And this is just coming from this, that if the theta here is pi, and then we'll see that e to the pi I becomes cos pi minus plus sine pi I, which is equal to minus 1. And then if we put the minus on this side, then the minus 1 on this side, then we've got e pi I plus 1 is equal to 0, right? So that is that for 6.4. Thank you.